This video explores the fascinating science behind how air conditioning systems harness the power of thermodynamics to keep your room cool and comfortable. Ever wondered how your AC keeps you comfortable on a hot day? In this video, we will break down the process and explain the science behind it in simple terms. Let's see how thermodynamics comes into play. Let us start from the basics of air conditioning. Air conditioning systems are designed to remove heat from a room and release it outside, making the indoor space cooler. The main parts of an AC system include the evaporator, compressor, condenser, and expansion valve. Each part has a specific job to keep the cooling process going. To understand air conditioning, we need to learn about the refrigeration cycle. This cycle is the fundamental process that allows air conditioners to cool indoor spaces efficiently. It involves a refrigerant, a special fluid with properties that enable it to absorb and release heat effectively. The refrigeration cycle has four main stages: evaporation, compression, condensation, and expansion. Each stage plays a crucial role in transferring heat from inside the room to the outside environment, thereby cooling the indoor air. The first stage is evaporation. The evaporation stage is where the magic happens. It all starts in the evaporator, which is inside the room you want to cool. The refrigerant here is a low-pressure liquid that absorbs heat from the air in the room. As it absorbs heat, it changes into a gas. This process cools the air around the evaporator, making the room cooler. The evaporator is designed to maximize the surface area of the refrigerant, allowing it to absorb as much heat as possible. It typically consists of a series of coils or fins that are exposed to the air in the room. As the refrigerant flows through these coils, it absorbs heat from the surrounding air, causing it to evaporate into a gas. The rate of evaporation is determined by several factors, including the temperature difference between the refrigerant and the air, the pressure of the refrigerant, and the flow rate of the air over the evaporator coils. By carefully controlling these factors, air conditioning systems can precisely regulate the temperature and humidity of the air in a room. The second stage is compression. After the refrigerant has absorbed heat from the air in the room and evaporated into a gas, it flows to the compressor. The compressor is a mechanical device that increases the pressure and temperature of the refrigerant gas. This process is essential for the next stage of the refrigeration cycle, condensation. The compressor works by drawing in the low-pressure refrigerant gas from the evaporator and compressing it into a high-pressure, high-temperature gas. This compression process causes the temperature of the refrigerant to rise significantly, often to over 200 degrees F, 93 degrees C. The efficiency of the compressor is critical to the overall performance of the air conditioning system. Compressors are designed to operate at high speeds and with minimal friction to maximize their output while minimizing energy consumption. Modern air conditioning systems often use scroll or rotary compressors, which are known for their high efficiency and reliability. The third stage is condensation. After the refrigerant has been compressed into a high-pressure, high-temperature gas, it flows to the condenser, which is located outside the building. The condenser is designed to remove the heat from the refrigerant and dissipate it into the outside air. The condenser consists of a series of coils or fins that are exposed to the outside air. As the hot refrigerant gas flows through these coils, it transfers its heat to the surrounding air, causing the refrigerant to condense into a high-pressure liquid. This process is facilitated by the lower temperature of the outside air compared to the temperature of the refrigerant gas. The efficiency of the condenser is also critical to the overall performance of the air conditioning system. Condenser coils are designed to maximize the surface area exposed to the outside air, allowing for efficient heat transfer. Some air conditioning systems also use fans to draw air over the condenser coils, further enhancing the heat transfer process. The final stage of the refrigeration cycle in an air conditioning system is the expansion stage, which is facilitated by the expansion valve. After the refrigerant has been condensed into a high-pressure liquid in the condenser, it flows to the expansion valve. This small device plays a critical role in reducing the pressure and temperature of the refrigerant, preparing it for the next stage of the cycle, evaporation. The expansion valve works by restricting the flow of the high-pressure liquid refrigerant, causing it to expand and cool. As the refrigerant expands, its temperature drops significantly, often to below freezing. This sudden drop in temperature is essential for the evaporation stage, where the cold refrigerant can effectively absorb heat from the air inside the room. The size and type of expansion valve used in an air conditioning system depend on factors such as the system's size and the type of refrigerant employed. By precisely controlling the pressure and temperature of the refrigerant, the expansion valve plays a crucial role in maintaining the overall efficiency and performance of the air conditioning system. The expansion valve works by restricting the flow of the high-pressure liquid refrigerant, causing it to expand and cool. As the refrigerant expands, its temperature drops significantly, often to below freezing. This cold refrigerant then flows back to the evaporator, where it can absorb heat from the air in the room and begin the cycle again. The size and type of expansion valve used in an air conditioning system depend on the size of the system and the type of refrigerant used. Some air conditioning systems use a capillary tube instead of an expansion valve, which is a small, narrow tube that achieves the same pressure and temperature reduction. The cooled air is then blown back into the room through a series of vents, providing a refreshing and comfortable indoor environment. These vents are strategically placed throughout the space to ensure even distribution of cool air, preventing any hot spots. The air conditioning unit typically has a fan or blower that helps circulate the cooled air efficiently, enhancing the overall comfort of the room. The process is continuous, with the refrigerant constantly cycling through the 4 stages to maintain the desired temperature. This continuous cycle is essential because it allows the system to respond to changes in indoor temperature quickly. For instance, when the room starts to warm up due to external heat or increased activity inside, the thermostat senses this change and signals the AC unit to start another cycle, ensuring the room remains at the desired cool temperature. Air conditioning systems also play a crucial role in dehumidification, which is the removal of excess moisture from the air. This is achieved through the condensation process, where the refrigerant absorbs heat and causes the water vapor in the air to condense into droplets. These droplets are then collected and removed from the system, leaving the air dry and cool. Evaporative cooling is another method used in air conditioning systems. This process involves the use of a wet pad or spray to cool the air. As the air passes over the wet surface, the water evaporates, absorbing heat from the air and cooling it down. This method is often used in conjunction with traditional refrigeration systems to provide additional cooling. At the end, we can say that the air conditioning systems are a remarkable example of thermodynamics in action. By harnessing the principles of heat transfer and the properties of refrigerants, we can create a comfortable and refreshing indoor environment. Next time you enjoy your AC, appreciate the sophisticated science and innovation behind its operation. Stay cool and see you next time.